All right, this is the start of the recording. Just talking for a little bit of volume check here. And yeah, 8:50 section on Tuesday, May 5th. There we go. I should move this here. There we go. Still have about a minute and a half. All right. Oh, still have a couple seconds here. Let's. Okay, welcome back. Move this over here. Let's take a look at the warm-up. So integral, definite integral from x equals 4 to x equals 5 of the function 6x over x squared plus 1 dx. Okay, this is a definite integral. If sometimes the thing to do for definite integrals is to think about it like an area and use area formulas. That's not the approach for this one. So we'll use a fundamental theorem of calculus, in which case I think it's safest to just always write the indefinite integral. So we're going to do this my preferred method. Some people insist on sticking with the definite integral all the way through. There's usually some errors of notation that pop up from doing this. I think it's just avoid that hassle. The indefinite integral is this. Right now we have this antiderivative problem. Sometimes to do an antiderivative problem, you need to just directly go at it without using substitution, right? Sometimes you need to do low algebra first. I don't think that's what applies here. This one is by substitution. Got to substitute here u equals x squared plus 1. Then the derivative, or du over dx, is going to be 2x. And when you solve for dx, you'll have du over 2x equals dx. So then let's go back and revisit this indefinite integral. And we'll substitute what we can. So we'll have integral 6x over u. And then the dx here gets replaced with this fraction du over 2x right there. Now, just in this, I would just like to point out here that sometimes the error that people make is they'll take 6x over 2x and will accidentally call this 4x. It's 6x over 2x isn't 4x. It's actually 6x minus 2x that would be 4x. And sorry to point this out kind of here and now, but like it's a common algebra error that occurs. And there was actually a version of this error that occurred on some rare instances during the exam. So I just thought it'd be helpful to point out, just to be careful of that. Oh yeah, speaking of the exam, I finished up some things this morning. I noticed a couple of people did sort of alternate solutions of things, so I needed to tweak up the key and grade according to an alternate solution. So that's posted. Please take a look at the key. The key is posted in Canvas. In any case, here, the factor of x on top and bottom cancel. 6 over 2, you can cancel a 2 on top and bottom. You're left with a 3 in the numerator. The u should remain in the denominator. That's a common. It's common for people to accidentally promote that u to the numerator or something like this. So we have here integral 3 over u du, and then this, now it's time to anti-differentiate. Okay, so then the 3 you can copy, and then to anti-differentiate 1 over u, that should be ln of absolute value of u plus c. And then one last step here is to replace the u with x squared plus 1. So you have 3 times ln of absolute value of x squared plus 1, close the absolute value, plus c. Well, that's the indefinite integral, right? So this finishes off the indefinite integral problem. All this work here was related to the indefinite integral. And now we can apply this. We can take this part right here. The circled thing there is the most convenient antiderivative when you plug in c equals 0. And you can use that, you can use this right here to answer the definite integral question which was originally asked. So we should take this antiderivative. This is the most convenient one anyway. I mean, you could use c as a different number, but why not use c as 0? We should take this right here and plug in x as 5 first, and then plug in x as 4 next. Be sure it's in that order. So you plug in x as 5 first, and you have 3 times ln of absolute value of 5 squared plus 1. And then after the minus sign, we have this same antiderivative. However, we plug in x is 4. So we'll have 3 times ln of absolute value of 4 squared plus 1. So that does it for the warm-up question. Hope that works for everyone. Just the kind of key reminders that I want to point out is if you want to use the other presentation method where you stay with a definite integral the whole time, that's your choice. Just there are things to be cautious of. If you have a definite integral that ends in a du in this problem, I don't. So over here, there's one definite integral written in this section, and it's right here, and that ends in a dx. But if you have a definite integral that ends in a du, then you have to be sure that the endpoints of integration are 17 and 16. So this would be correct. There's a du here, and there's a smiley face here to indicate, right? So you have du, and then the u values are 17 and 26. That's fine. The error that sometimes is made is people will take this integral 3 over u du and leave the 4 and 5. They'll just keep copying the 4 and 5 over. That would be incorrect. The other thing that'd be, I mean, kind of one stage earlier than this would be this one over here. And if you had a du, and I screwed up the screw up here, so I'll fix that when I post this. But it would be an error to have a 4 and 5 on this integral as handwritten in. It would, again, here need to be a 17 and a 26. Okay. We'll do a round of announcements now. We'll repeat these at the end. Today's a Tuesday, so please look at the online quiz that's posted for today. There's a final quiz on Thursday as well. I would say please keep current with the web work. I know it's late to plead and ask these things, but I think it's good to do to at least start, even if you don't finish, to at least start web work number 43 today. The final due date for WebWork 43, however, it is during finals. So it's on the Monday of finals week. And for that reason alone, I just decided to make the WebWork set extra credit. Only because of when the final due date is. This is a thing that happens some semesters. There's trade-offs between talking about a thing in class that day and then making it due that night. Oh, I don't personally appreciate that approach, because then there's an expectation that everybody gets everything right away. So there's a downside to talking about something in class and then making it finally due almost a week later. It's 6 days later, next Monday. That was true all semester long, right? So there's pros and cons, but just wanted people to have time to visit office hours and things like this. But it does in this case mean that there's an assignment that spills into being due kind of much later than I like during finals. I know that's inconvenient, and that's why I just decided to make it extra credit. I would still do it, especially because it is extra credit. Office hours for the remainder of the semester are posted. If these times don't work, send me an email. We'll set up an appointment. Final exam, available starting May 12th, needs to be turned in by the end of the day on May 13th, and you pick your own 6-hour window of time to work on it. Today's big idea, I don't think it's actually so bad. We've done way more complicated things. So if this first example kind of works, then I think you'll be okay for today, and tomorrow for that matter, right? So here it is. So let's just dig in, right? So you got this function, f of x equals x squared plus 1, and this other function, g of x equals x over 2. So the question here is, what's the area between these two graphs? Starting at x equals 6 and then ending at x equals 10. So I'll just do a really rough sketch of this first. Y equals x squared plus 1. Well, okay, y equals x squared, that parabola, and then plus 1 shifts it up 1 unit. So just even as a very, very rough picture, what we should have is like, there's 1 and a parabola, something like that, okay? And then, yeah, it should be more balanced than my picture is here. And then you have this y equals x over 2. Actually, another way to write this is y equals a half x. Maybe that makes it just a little clearer that this is really a y equals mx plus b. Right? This is, I know it was written a little funny as a y equals x over 2, but it's really slope is 1/2, y-intercept is 0, so it's a shallow line. Y-intercept is 0, meaning it goes right through the origin. Shallow line like that. Okay, should be a straight line. My picture's not also good. This parabola, by the way, sometimes people draw this too sharply this way. Sometimes people draw it, it doesn't. Again, this is a rough picture. Sometimes people draw this a little more shallow. The key thing is sometimes people draw this so sharply that when you have x equals 6 here and you have x equals 10, some people's drawings are too sharp that like this x equals 10, it does actually cross the parabola at some point. It has to. It in fact happens when the y value is 101. So I'll just draw these two vertical lines in here, and the region that's between the graphs of f and g, so that should be like this part right here. This is a rough picture, right? Like it's not entirely accurate, but it's enough of a picture to see what's happening. I do have a computer rendition of this that's much nicer. So you'll notice that here the y value 101, I had to, so this picture's very squashed just in terms of size, because the y coordinates go all the way up to 101, x coordinates we only needed up to 10. So this picture's not really to scale, but the thing is the shaded region in yellow here, that's what we want, right? The question here is how much paint for that yellow region. We want the yellow region only. Now here's the thing. The problem is, okay, there's this graph f, the parabola. Here's the graph g, and we want the region that's in yellow only. And if we set up the integral of f from 6 to 10, right? So there's f again. If you set the integral from 6 to 10 of f of x dx, you get the area under the curve. And I mean, so you get the part that's in yellow and the part that's in blue, right? Set up the integral of f, and we get not just the yellow region that we want, we also get this blue region that we don't want. That's a problem. Well, what we should do is this blue region, right? So, sorry how that's written. This blue region, there's G, it's that straight line, a very shallow slope of 1/2. That blue region is actually the integral of g from 6 to 10, and it's the region that we don't want, right? So this first integral over here, it's the yellow and blue regions combined. The blue region down here, it's the integral of g alone, and so the yellow region that we want should just be take the integral of f from 6 to 10, subtract away the integral of g from 6 to 10. And that's the big idea today. It's there's one integral, which is this entire thingy here, but we don't want all that much. We only wanted the part that's in yellow, so we had to subtract off the area that's in blue. This is one way to write it, one integral minus another, but it becomes kind of more work to keep track of two integrals, so we can actually use one of the properties of definite integrals to squish this together and call this the integral from 6 to a single integral from 6 to 10 of f of x minus g of x dx. So f minus g is the thing we're integrating here. The key thing here is that f needs to be the one, needs to be the curve that's above. So f is up here, g is down there. And that, just this by example, this exploration leads to this idea. Here's the key idea today. Area between two curves. So if you have f of x is greater than or equal to g of x for all x in an interval from a to b, then the area between the graphs of y equals f of x and y equals g of x, and between the two vertical lines x equals a and x equals b, it's given by this. Right? So this was the idea we sort of were discovering by example just a moment ago. And that area we'll call capital A here. So that's it. That's really it. And we'll look at examples in a moment, but I just have a couple comments about this formula first. So first of all, this first piece of text here that says f of x greater than or equal to g of x, that just, in terms of a picture, geometrically just means that the graph of f is above the graph of g. And we saw that example in the last problem. So the thing is, if f really is greater than or equal to g, then f of x minus g of x is always bigger than or equal to 0. And that means if this thing right here that you're integrating, it's a property that we have not dug into a lot, but it turns out that if what you integrate is always greater than or equal to 0, that definite integral, the value of capital A always has to be greater than or equal to 0. So the reason I want to bring this up is when you look at just integrating a single function, you get something different. So in this case, when you look at, and you always have, if you have the setup of the upper function minus the lower function, if you guarantee you've got that, then this integral always gives you an area in a positive sense. But to contrast that, when you integrate a single function, it sounds bizarre, but if you integrate a single function, f of x, you get a signed area. But when you integrate one function minus the other function, and you know for sure that the f function is above the g function geometrically, then this integral, the integral of subtracting two functions from each other, will give you a positive area. So I'd like to do some examples. Okay, so first example, integral, sorry, not integral yet, we'll set up an integral. Question, what is the area between y equals 1/2 x and y equals 3 to the x plus 4 from x equals 2 to x equals 6? So we'll do a rough sketch of this. I'll just actually draw this out. Sometimes your rough sketch, sometimes it's actually more helpful to draw in axes. Sometimes it's less helpful to draw in axes. You just kind of got to get used to this a little bit. So first of all, 1/2 x, well, that's the same line we just spoke of earlier, right? Slope 1/2 going with y-intercept of 0, therefore going through the origin. So a shallow line, something like that. You have this y equals 3 to the x, so that's an exponential function. I want you to be familiar with what that looks like from an algebra class. Plus 4, shift up 4 units, right? So you get a graph that, at least roughly speaking, looks like that. And then from 2, x equals 2 to x equals 6, so you draw vertical line, and the region we're talking about that's between, so it should be below the, it's below the exponential curve and up, right? So this shaded region, we shaded below the exponential and then above the line. So the key thing here is, even almost without drawing, if you're familiar with the graph of the exponential and just how quickly the y value grows, I want you to already see that this is the one above, and then this is the one below, right? Y equals 1/2 x, that's shallow slope of 1/2. And I want to be clear with what I mean by above, and I'll have to emphasize this because this is the part that's confusing, I think, for people, is in this shaded region. If you just start anywhere in the middle of it, if you walk upwards, you go up, you end up at the very top of this, you end up reaching the exponential. If you started it sort of somewhere again in the middle of the shaded region and you walked downwards, you would end up hitting the line. And we're talking about which one's above, which one's below. So yeah, again, I wanted to put some words to this in the slide. So you've got a line and you have an exponential that's been shifted up. I actually have a picture, a more accurate picture of this that I want to click I already clicked on the link. You can click on it later if you want to explore more. But here it is. So you have this exponential in blue, 3 to the x, then plus L4. You have this line, y equals 1/2 x down here in red. It's very shallow, and in fact, the x-axis, I don't know if you can see here, it only goes up to like x is 12. The y-axis, I had to like go up to y is 700 just to be able to show what's going on in this picture. This region, so sorry, the y-axis represents way more numbers. The scaling between the x and y-axis is off. The region we want, it's shaded here in purple. And again, the thing is the exponential function is the one that's above. Right? So let me do that. So the point is, even with a very rough sketch, I want you to see this idea that the exponential function is the one that's above. And so if we set up an integral, it should be the upper function, the one that's above, minus the lower function. Minus, and the lower function being this very shallow sloped line of 1/2 x. And then we integrate this from, well, we were provided these x values in the question, x equals 2 to x equals 6. So there, and there. Okay. Let's see. What do I want to say? Oh, so then how do we actually get a number for this area? Well, we have this definite integral. What we should do is then look at an indefinite. To find the area, we should look at an indefinite integral, right? So I just took the same problem, put it right here. Notice that I could drop all the parentheses without changing any of the meaning. And then I just left off the 2 and the 6 to talk about the indefinite integral. This is an indefinite integral. You don't have to do any u substitution, anything like that. Just each one term at a time. Anti-differentiate 3 to the x. Anti-differentiates to become 3 to the x over ln of 3. 4, its antiderivative is 4x. Copy the minus sign. To anti-differentiate 1/2 x, I copy the 1/2, and then the antiderivative of x is x squared over 2, and then there's a plus c here. Now that we have this antiderivative, I'm going to take this part right there and go back to the definite integral up here and plug in a 6 first and then a 2 next. Right? So the definite integral, I just copied this over here. I took this circled antiderivative and plugged in x is 6, and then I plugged in x is 2. Okay, so this number right here, it happens to be positive. That represents the purple region that we saw in the picture a moment ago. Now here's the thing. Today, partly in the interest of time, it's like the integrals that we're setting up today actually are not so bad to work all the way through. So we're not going to work them all the way through. The bigger thing, the thing that tends to cause people some issues today is the getting familiar with graphing, right? Some of the rustiness with that. So the thing to do today really is say, let's just get to this as a stopping point today, right? Like I don't want to keep completing these integrals, especially when we've seen much more challenging integrals than the ones we'll see today. So today the focus is not on computing the integrals. We'll look at each question, we'll talk about the graphing issues that tend to come up, those challenging issues, and set up an integral. Set up the correct integral. As far as doing the integrals that you're seeing today, they're not bad. None of them even require u substitution. Like they're much nicer integrals than the ones we've seen. So let's run through another example. Unless I should step back. Unless there's questions on the example we just looked at. Okay, so let's look at the next example. So what is the area between y equals negative x minus 4 and y equals x squared plus 3 and x equals 10 and x equals negative 1? So first of all, x equals 10, x equals negative 1, those are two vertical lines, right? Yeah, vertical line, vertical line. Yeah, x equals just a number, x equals a fixed number, those are vertical lines. We've got here, this is a line. This is a y equals mx plus b, right? The m here is negative 1, slope negative 1. The b, the y-intercept is negative 4. This other one is a parabola. Y equals x squared plus 3. Think about it. Like y equals x squared is kind of that standard parabola. Plus 3, you shift up. So I mean, even without having drawn, I just kind of spoke through it. But like already, you should look at these four things and just think to yourself, okay, line, parabola, vertical line, vertical line, right? Let's take a look at a picture, but actually even before clicking to look at the picture, if you just did a very rough sketch, with or without axes, like I'll just draw axes this time because these are not so bad, but you've got like y-intercept -4, slope -1, looks roughly something like this. Parabola, standard parabola that's shifted up 3 units, probably something like that. Does the line intersect the parabola? Maybe, maybe not. X equals -1, like right about there. And then x equals 10. Maybe it might be further out to the right, but like I only drew this much of the parabola, so we're just gonna fake this by putting 10 right there. And I barely even have enough room for where the intersection with the line is, but it should intersect somewhere. So the region we're talking about, roughly speaking, looks like this. Right? This is a rough picture. Here's a much better picture using the computer. Again, what you're seeing is the scaling is off. So the x-axis goes from -4 to 12 roughly, while the y-axis goes from -20 to 100. Okay, just to be able to fit the picture again. But you'll see that just like in the picture we drew, the parabola is above. The line is below. The region that's shaded here in purple, parabola is above is the key thing. Right? That's the whole purpose of drawing the picture. If the parabola is above, then we set up an integral. It's x squared plus 3, the parabola formula, minus -x minus 4, the line formula. And then, right, so you don't want to swap these two accidentally. It's got to be x squared plus 3 first, and then after the minus sign, you need this -x minus 4. And then the next thing is the x values. Well, we stick the smaller x value, which was -1, down here, and then the bigger x value of 10 is up there. Now, one other thing is this set of parentheses right here, x squared with x squared plus 3, is you could drop that set of parentheses. However, the parentheses around quantity -x minus 4, those parentheses are required. Why? Why are those parentheses required? Let's think about that. Why would those parentheses be required? So the thing to note, yeah, is that here this is two terms, and we're subtracting. Right? So this is an order of operations issue. Right? So the reason is because there's more than one term, and it's behind a minus sign. So though you could drop these parentheses, here the parentheses are required. How's that for this example? Okay, I would like to then ask if you would take a moment to try these. So there's two separate questions here. It's just integral setup. You don't have to go all the way through to get the number here, right? So set up an integral for, first of all, the area between y equals e to the x and y equals -x and x equals 3 and x equals 4. That's the first one. And then the next one is set up an integral to represent the area between y equals 5 minus x squared and y equals x squared minus 13 and x equals -2 and x equals 1. And I'll give you a moment to work on these, but then in several minutes the rest of the slide has some of this worked out. Okay, let me say a word about maybe the first one and just draw like a very brief sketch of, I'll go ahead and include axes for this one. I think that's actually helpful for this one. Y equals e to the x is an exponential function. So like all the other exponentials, you know, y equals 2 to the x, y equals 3 to the x, y equals e to the x, they all kind of look like this with a y-intercept of 1. And then y equals negative x, well, that's a line, right? Slope is -1, y-intercept 0, so going right through the origin. So that line, you know, like that. X equals 3, x equals 4, so let's see, somewhere over there on the positive part of the x-axis, they're just right next to each other, these two vertical lines. And so we should have a region that looks like this. The point of the picture is to just clear up that the exponential is the one that's above, right? And in fact, here's the thing: the exponential curve is in the first and second quadrants, and for x values between 3 and 4, this line y equals negative x is just in the fourth quadrant as we saw. So it's like, even without too much of a drawing, like there's a, you know, just being familiar with what an exponential curve ought to look like, we're like, oh yeah, the exponential is the one that's above. The line is the one here that's below, right? So here's a picture. Again, not the y-axis and x-axis are not on the same scale, just to be able to fit the picture in. And the region we're talking about is there, right? So in this shaded region, you've got to walk upward to get to the exponential, and you walk downward to get down to the line. So setting up this integral, it should be, well, 3 to 4. Okay, those were provided. The smaller number 3 is written down here first. And then so then the upper one was the exponential, and then we subtract the lower one, so this negative x. So there's these two minus signs here. Strictly speaking, you don't even need to draw parentheses here, just because there's only one term. But just because it's a minus and a minus, sometimes it's visually nicer to draw the parentheses, so the parentheses aren't required, but I drew them in. Let's just, to clear up that there are two minus signs, let's just clear up that this minus sign right here is because the formula here had a minus sign in it, whereas this minus sign, this first minus sign was because it was y equals negative x. We just had to copy that. This other minus sign right here, the one right after the e to the x, is because the formula for the area between curves has a minus sign. It's the upper formula, it's the upper function minus the lower function. Emphasis on the word minus there. Okay, of course, if you'd like, you could write this as integral 3 to 4 e to the x, and then minus minus, you convert that to a plus, then x dx. And this would be like more some of the work you do if you're actually going to now go find the number. But again, today I want to focus more on just setting up the integral. Talk through what do the graphs look like and this sort of thing. If you look at the next one, you have a parabola that's upside down, right? And by upside down, I just mean, like, you know, from the usual y equals x squared. Why is this upside down? Because you see that the number in front of x squared is -1. Right? With a coefficient of -1, that parabola should be upside down. The other thing here, y equals x squared minus 13, that's a parabola that's sort of in the usual direction, right side up, because the coefficient in front of x squared is this hidden 1. So you have a upside down parabola and a right side up parabola. Upside down parabola, you know, shifted up 5 units. You have a right side up parabola shifted down 13 units. So already, like, I didn't draw axes this time, but like already, just based on you have an upside down one and then you have a right side up one, it should be the upside down parabola that's above. Like, it's just visually that's got to be the one that's above, even without drawing axes. And then you have this x equals -2 and x equals 1 provided. Okay, so I do have a picture to show for that as well. Let me just pull that up, and then so the upside down parabola y equals 5 minus x squared is shown in red. The right side up parabola shown here, right? So it really is, and here's the shaded region. We were provided by, you know, if we go back in the question, we were provided x equals -2 and x equals 1. So we were provided these x values that created these two vertical lines. The region we're talking about in the question is the region shaded in purple here. So we just need to set up an integral of the upper 5 minus x squared then minus the lower, so quantity x squared minus 13 from x equals negative 2 to x equals 1. Now, one thing to note about this is the red curve, in this purple region, the red curve is the one that's above, but the red curve isn't always above, right? This red parabola and this blue parabola, they intersect each other at 3 comma negative 4 and negative 3 comma negative 4. So the thing is, we have to actually be a little careful that, like, what if, I mean, I'm going to just move this for a moment, but if this x value were over here, you know, there's some things we have to be a little careful of. And it's a good thing that the two x values that we were provided, they were, again, negative 2 was provided in the question, 1 was provided in the question. It's a good thing that those x values are between x equals negative 3 and x equals positive 3. So we didn't have to worry too much here about funny business, but I just want to warm you up to this idea that we've got to be a little careful. And let's talk about a little bit. First of all, let's set up this integral. The upside down parabola. So integral of upside down parabola minus the parabola that was below was the right side up parabola, x squared minus 13. That one has to be in parentheses. And then the integral is set up for x values from negative 2 to positive 1. Okay, so that's setting up this integral. But this sort of strange feature that came up was, how could we have come up with the intersections of the two parabolas? That the intersections we saw using the graphing tool was x equals plus minus 3. How could you find this? Well, you can do this using algebra because you've got y equals 5 minus x squared and y equals x squared minus 13. You can set those equal to each other and solve. So there's a way to do that. This idea of actually finding these intersections, right? This algebra way of seeing a geometric idea is going to come up, in fact, in the next question. So let's give that a try here. So I'd like to find the area enclosed between y equals x squared minus 2 and y equals x plus 4. That's the end of this question. You'll notice it's kind of different from other questions we've looked at so far, because in the other questions we were provided 4 things. We had 2 functions, we had 2 x values. But here it's just one function and another. But let's think about what we should have shape-wise, right? So y equals x squared would be a parabola, minus 2, shift down 2 units. You've got y equals x plus 4. That should be a line with slope 1 and y-intercept 4. So just first of all, overall, the picture is we have a parabola and we have a line, and that line has positive slope. So if they intersect at all, it's probably a picture that looks like this, right? So the area enclosed, it's like this region right there. So the point is, in this shaded region, the thing that's above is the line. And this is the part where I think people sometimes get a little confused. So let me try to erase, and I'll have to redraw part of the picture here. Let's try that again. So in this shaded region that's here, what do I mean? What I mean by the line is above is if you start as a point somewhere in the shaded region and you travel up, you end up hitting the line. So the line is above. If you start again somewhere in the shaded region and then you walk downward, you end up hitting the parabola, the curve. So the parabola is below. See, that changes a little bit later on, but like over here, it's the parabola that's above, right? So in this shaded region, though, it's the line that's above the parabola that's below. Okay, so the point is, right now, we've got a concave up parabola. We have a line. It's the parabola that's below, the line that's above. And here's the thing. In this question, we weren't given x values. So, yeah, the line's above, the parabola's below in the enclosed region here. But what should a and b be? Right? So how should we know what those numbers a and b are? So we've already set up most of this integral. But the thing above would be the line. So the line x plus 4 is there, and the parabola x squared minus 2 is here after parentheses, or in parentheses after the minus sign. But how do we know what x values? Well, we need to see where these two curves intersect. So we already sort of drew a rough picture even without axes drawn in. We need what's the x coordinate there and there. So we need to see where the line and this line and this parabola, where they intersect. So what we'll do to see where that occurs, we'll set the y's equal to each other. We'll set equal x squared minus 2, set that equal to x plus 4. So we have this equation to solve. Solving this equation is going to tell us where these two curves intersect. So subtract x on both sides, subtract 4 on both sides. All the integers have having a 0 on one side of this equation. This should factor. It does, right? X minus 3 times x plus 2 equals 0. And because you've got a product equaling 0, you can set each individual factor equal to 0. I meant for this to be on its own line. Little typo, I'll get that fixed. But you end up with x minus 3 equals 0, x plus 2 equals 0, and then solve each of those little equations. You have x equals 3, you have x equals negative 2. So those are the two x values. Those are the places where the two intersections occur. So we can set up the integral now. Right? So this area, now that we know what a and b should be, they should be 3 and negative 2, but in order. So the smaller x value is down here. Negative 2, then 3. Now, here's the thing. We did all of this with just a very, very rough picture in mind, right? It didn't draw any x or y axes. It just was like there was this parabola that was provided. There was this line. So in the shaded region, if there is this shaded region at all, in the shaded region, the line has to be the thing that's above and the parabola below. So line above, parabola below. We set the y's equal to get these x values and put those x values as the endpoints of the integration. But we can see this all also in a picture, like using a graphing tool, we can see all these features. So I wanted to show you that. And what I wanted to do is in this link, I've done things a little differently from the other ones. I wanted to simulate. I want you to go back for a moment. Like I left the link towards the end of this one intentionally because it's like more realistic for how we would actually attack these questions. But imagine we're back up here in this stage where we're like, okay, the line is above, the parabola is below, but we don't know what the x values are. So let's just, I tried to simulate that in the link by just guessing random x values. So let me show you what I mean. I've got here, first of all, the graph of y equals x plus 4, y equals x squared minus 2. Those were provided in the question. And the region that we really want is shown here shaded in blue. That's what we really want. But what I've done is I've just said, oh, x equals a, x equals b, and I just created some sliders that have some just random x values. Right? I picked a to be the x value 0.4 and b to be the x value 1. And you'll see that shaded region here in red, that's not what we want. We want the blue shaded region. So we would need to change this first starting x value of a to not be 0.4, to be something else. And we see, at least using the graphing tool, that the correct x value to use here was 2, and then over here that the correct x value to use right there should be 3, right? But we discovered, so I mean, we could have done this graphing tool first to have discovered the x values negative 2 and 3, but I wanted to postpone using the graphing tool so that we could really see, aha, we could discover this information without the use of that tool. Like we just had to set the y's equal to each other to see where those intersections are. All right, so then let's do this, unless there's questions. Okay, I'd like you to please take a moment to try that. Set up an integral for the area between y equals 5 minus x squared and y equals x squared minus 13. Again, think rough sketch first, maybe even a sketch that doesn't involve drawing x and y axes. Just what would that roughly look like? And notice you were not provided x values here. Okay, so the thing to note here is we've got this parabola with this negative coefficient and a parabola with this positive x squared coefficient. I actually wanted to just use slightly different language. We could talk about upside down and right side up parabolas, but we've got calculus language we can use for this as well. So like this 5 minus x squared, just to use new language and start providing reminders of things, it's concave down. It's a parabola that's concave down, right? Because if you took a second derivative, we could even probably do this in our head, right? So second derivative, first derivative is negative 2x. Then the next second derivative would be negative 2. Well, negative 2, no matter what you plug in for x, because there's no x to plug in for, that's concave down the whole time. It's a parabola that's upside down, so to speak, right? So you've got that. And then x squared minus 13, take a second derivative, you get 2. And so that's a concave up parabola. So we see that these two parabolas end up trapping and closing this region, and the concave down parabola is the one that's above. The concave up parabola is the one that's below. So already in setting up the integral, we're so close to done. It's an integral from a to b. We don't know what a and b are yet. We'll get those in a moment. But what I'm trying to point out is that the concave down parabola, the one that's above, should be written here first, this 5 minus x squared. And then after parentheses, in parentheses after the minus sign, we need the concave up parabola, because that's the one that's going to be under. That's the one that's below. Then the things are, what about the x values? So we need to find where those intersections occur, so we should set the y's equal. Right? So set 5 minus x squared, which is y, equal to x squared minus 13, which is y. It doesn't matter the order. I just found it a little more convenient to write the x squared minus 13 first. And to solve this equation, I'm going to add x squared to both sides. I'm also going to add 13 to both sides. So you have 2x squared equals 18. Divide both sides by 2. You have x squared equals 9. Square root both sides. You have x equals plus or minus 3. Please be careful here. Sometimes what happens is when people square root both sides, they just get x equals 3. Well, that's only one value of x. You might say, well, how am I supposed to set up this integral with only one value of x? It's because there's more than one value of x. Whenever you square root both sides of an equation, there's a plus or minus sign. So those two values of x, negative 3 and positive 3, are what end up here and there. Right? So we have this integral from negative 3 to 3 of upper function minus lower function. And in fact, I do have a link just to show for that. So here's what that picture looks like, right? So the upper function really is the concave down parabola. That's the 5 minus x squared. The concave up parabola is the lower function, right? It's the lower part of the shaded purple region. It's the very bottom edge of it. And we see here, in fact, that so even though we were not provided vertical lines x equals negative 3, x equals positive 3, those are the places to stop because that's where the intersections occurred. If we set up the integral accidentally to go up to x equals 4, for instance, I just made up a number, then we'd get this extra region over here. See, this would be like it would look more like one of those cartoon fish drawings. Like you'd have this region right here in purple, which we want, and then you'd have this like extra region that almost looks like a triangle. It's not, but like it would be like the fish tail, you know? Like we don't want that part, right? So we have to stop. If we only want the region in purple, we have to stop right there at x equals 3. Okay. So with that, let me just say a couple things, a couple kind of quick things, and wrap up with announcements and so on. The thing is, tomorrow we're going to look at a situation like this. We're going to have like, there's two functions provided. They're shown here in red and blue. And maybe we're looking between x equals 2 and x equals 10. And we will be tomorrow asked the question, find the area. Well, there's this region and this region, these two regions, and you'll notice the red curve isn't always above. For that matter, the blue curve isn't always above. Sometimes the red curve is above, sometimes the red curve is below, sometimes the blue curve is above, sometimes the blue curve is below. The fix for this situation, which we are not dealing with today, but we will look at tomorrow, it's actually not that bad, right? So the fix here is just this x value right here, right where this intersection of the red and the blue is. That's interesting, right? So all we need is that, because then we can set up one integral. Like this part here will just be an integral from 2 to whatever number this is, whatever the x value here is, integral 2 to that x value of the blue formula minus the red formula. And then we add to that a separate integral of an integral starting at whatever this x value is, ending at 10, to get this other region of the red formula minus the blue formula. So it's just still the upper function minus lower function. Sometimes, though, due to how the nature of the graphs go, we need to set up two separate integrals. We'll look at that tomorrow, right? So tomorrow we're looking at the situation when one curve isn't the one that's always above. And then the other key thing we're going to do tomorrow is the topic that, one of the topics that had to be cut is area. So what's an application of this area between curves? I wanted to just talk the application, and it's an application that comes from economics, but the application on its own wouldn't have made sense without what we're doing today and tomorrow. So I felt like it would be better to build up the math skill of computing or setting up integrals to represent the computation of the area between two curves. And then we'll just, in the last 5 minutes of tomorrow, at least just in a cartoon format, talk about what's an application of this. And you won't be responsible for that application in this class, like not in a quiz or test or anything like that. But it's just good to know so that when you take an econ class, as most students in here are CBA students, when you take an econ class that talks about producer surplus and consumer surplus, you can make all those connections and make things ready to go. What you'll notice, though, today is that graphing is a key thing, right? Like, if you actually look back throughout the entire semester so far, every aspect of algebra really appeared somewhere in this calculus class. The thing that hasn't appeared a whole lot is graphing. And I would say, for some certain functions, that very typical ones that you'd see in an algebra class, they're the kinds of functions I want you to be familiar with for this section. So like a 5-second sketch, right? Like be familiar with what an exponential function like 2 to the x looks like. E to the x looks morally the same. Sometimes people just freak out because the exponent is e. I should point out that e to the x and ln of x, these are not the same. These are not equal. They're related. They're inverses, so they're diagonal flips of each other. And then same deal, 2 to the x and x to the 2, those are not the same, right? So this is an exponential. X squared is a parabola. X squared minus 9x is a different parabola. X squared minus 9 is a different parabola from those. And then 2x minus 9 isn't even a parabola. That's a line, right? So we'll kind of dig into some of these tomorrow. And the point is, some of I don't think this section it's not conceptually challenging from a new calculus standpoint. The thing that tends to get people is the graphing. And that's why you heard a huge emphasis on sort of like, you may be rusty on some of the graphing. And wanted to point out some features today in that, and we'll do that again tomorrow. Just a reminder, today's Tuesday, so please do the online quiz, and see you tomorrow.